The offshore wind sector faces a number of challenges in its future development. 80% of offshore costs is attributed to accessibility and transport when completing asset integrity inspections. Engineers are faced with specific transport windows due to the dynamic and rapidly changing weather conditions, which presents risks in an already challenging environment. Offshore wind turbines are being constructed further from the shoreline, increasing the difficulty, duration and costs associated with offshore inspection. Lastly, there is also a recruitment shortage in the offshore renewable energy sector at all skilled workforce levels. The value of robotics and AI can be captured industry-wide. Robotics and AI is a rapidly developing field which looks to tackle these challenges in the offshore environment. Several technological, regulatory and commercial barriers limit the expansion and full exploitation of robotics and AI in the offshore domain. Runtime safety and reliability of autonomous systems are key obstacles to ensure resilient, beyond visual line of sight missions. A key factor in unlocking the future potential of robotics is how can a robotic platform self-certify their systems and update human operators that they are fully operational and ready to go. The remote and dynamic environments that autonomous systems will be required to navigate often mean that it is not always possible or feasible for human operators to interact with a robotic platform during live operation. Therefore, systems require autonomous adaptive mission planning, which can take into account known and unforeseen circumstances that could influence mission success or cause safety, environmental or asset-related risks. These barriers represent a complex representation of integrated systems and engineering challenges wherein time-critical analysis is required to ensure productivity, reliability and safety governance. Robotics and autonomous systems require a symbiotic system-of-systems approach to resilience in autonomous missions. We have defined a symbiotic system as the lifecycle learning and co-evolution with knowledge sharing for mutual gain. A system of systems is defined as a set of systems or system elements that interact to provide a unique capability that none of the other constituent systems can accomplish on its own. This approach is driven by the view that to improve operational situational awareness via bidirectional knowledge exchange from a digital twin will optimise performance and encourage lifecycle development. This can be completed by aggregating information from across the infrastructure, environment, robot and human in the loop. The challenges which symbiotic systems face are how to create a collaboration interface which facilitates trust from the human in the loop, in addition to providing an improved autonomous system overview to classify mission status, system certification and data sharing without overwhelming the human in the loop. The solution to this problem facilitates functionality, human trust, increased autonomy, operational resilience, and compliance certification. We design a symbiotic system of systems using a top-down assessment of these barriers to create a framework that includes functional, operational, planning, and safety requirements of resilient autonomous missions. Our symbiotic systems of systems approach addresses the previous barriers between collaboration, cooperation, and corroboration of autonomous systems. Our approach enhances this via the integration of collaborative governance under our symbiotic digital architecture. This demonstration focuses on Tier 1 Adapt and Survive with a roadmap to Tier 2 Adapt and Thrive. Tier 1 represents an autonomous mission or service with predefined mission objectives, where the robot evaluates the following: the implications of a scenario from operational variables, sharing knowledge with the digital twin, and mitigating threats to mission resilience. The symbiotic system was applied to our autonomous confined space inspection showcase using our robotic platform, Husky A200 mounted with a pair of UR5 manipulators. This required a system integration process and symbiotic digital architecture to ensure mission success. The system integration process represents the features of the subcomponents of the symbiotic system. The layers display the links between all subsystems and highlight the demonstration variables which are being addressed. The human in the loop represents the human interaction layer where the operator can interact with mission components within the digital twin. The decision making is linked to the simultaneous location and mapping stack, motion planning, and ontology. The digital twin is connected with the Fmcw sensing, which is utilised in the confined space autonomous inspection mission. The digital twin represents the user interface layer, which contains the tools and functions for the human in the loop to have an overview of any autonomous systems. The decision-making planning domain definition language layer of the runtime reliability ontology is linked to the key software systems of the robotic platform. The ontology processes diagnostic data from the internal sensors of the robotic platform. The SLAM stack receives data from the LiDAR sensors and cameras. The motion planning calculates the commands to be sent to the mobile base and the manipulators. To support resilient autonomous missions, we have focused on the integration of the top-down requirements, as well as ground-up capability challenges. For the information from an autonomous robotic platform to be actionable within a time-critical context, it must be mapped into a design for resilient systems through our symbiotic digital architecture, which captures functional, operational, safety compliance, and planning requirements. Our symbiotic digital architecture commences by supporting the remote human observer, enabling for access via a real-time, bidirectional, and interactive digital twin. A meta-function of the digital twin includes a ghosting function, which increases safety by reducing the risks associated with the manipulation operations. A runtime reliability ontology supports adaptive mission planning, enabling for front-end resilience via runtime diagnosis, prognosis, and decision-making. Within the design of our runtime reliability ontology, we feed front-end data analysis and edge analytics into these back-end models within the digital twin. To enhance situational awareness, we integrate a novel radar technology for asset integrity inspection onto the robotic platform. Frequency modulated continuous wave Fmcw radar provides surface and subsurface asset integrity inspection. Presented as the inspection overview in a 3D model. Stage A represents a reconnaissance mission to map the area where the autonomous platform will be deployed, represented by the white map on the ground of the model. Stage B and C represent the mission base point and transit of the mission. The asset integrity inspection is performed at Stage D. Stage E represents the transit through the confined space. Stage F is where the second asset integrity scan is performed. And then lastly in Stage G, faults are induced on the robotic platform. These faults represent the motor being too hot, the software consuming too many resources, and a low battery fault. When mission planning, the human operator sets out green dots for waypoints. The robotic platform optimises the route automatically upon starting the mission. Here we see the asset integrity inspection using the Fmcw radar mounted on the front of the robotic platform. The non-destructive inspection is assessing for corrosion on the metal sheet. Upon completion of the first asset integrity inspection, the robotic platform moves through the section of the route which is considered as a confined space operation with respect to the size of the robotic platform. For this demonstration, the standard assigned proximity warnings had to be removed and replaced with narrower warnings to allow the robotic platform to enter the confined space. The runtime reliability ontology is pictured, highlighting the complexity of the fault prognostics. The second asset integrity inspection is completed where the fast Fourier transform data collected from the Fmcw radar sensor is displayed. The robot then returns to base where faults are induced on the platform en route, where in real time the ontology replans if mission success can be achieved after receiving each warning. The warnings include an increase in temperature of the motor, software consuming too much resources, and lastly, a low battery warning which automatically ends the mission. The stages of the mission are represented within the displayed flowchart. The pre-planning mission requires a human operator to teleoperate the robotic platform to accurately map the area where the autonomous inspection will be taking place. With the map established, the human operator can position waypoints and assign tasks where necessary. Upon completion of the pre-planning stage, the robotic platform receives the mission from the wireless base station. The optimum mission route is then calculated by the robot. In Stage C, the robotic platform completes its autonomous navigation until the waypoint is reached. The first asset integrity inspection is performed in Stage D, where the pan tilt unit is repositioned to face the material under test. The Fmcw radar sensor is turned on to complete the number of required scans for the non-destructive evaluation of corrosion. The data is transferred via bidirectional communications to the digital twin in real time. The autonomous navigation then repeats to the next waypoint. For the second asset integrity inspection, the same set of instructions are performed by the robotic platform as in stage D. The robot is programmed to return to the base in stage G. However, we induce several warnings on the robotic platform to verify the resilience of the AI-supported runtime reliability ontology of the robot. We induce a motor temperature increase where the following decisions are made by the robot. First, the ontology identifies if there is a fault which requires the immediate safety stop of the mission. If not, the ontology identifies if the temperature is above the warning threshold to prompt the human operator of the potential risk. This updates the human in the loop in real time where the robot continues with the autonomous mission. Secondly, we induce the software consuming too much of the resources. The ontology assesses if this is within the fault threshold and should make the decision to stop the mission. If not, the risk is assessed as within the warning threshold. The human in the loop is updated in real time via the digital twin about the risk where the mission continues. The last warning in section G of the mission includes a low battery fault detected. The procedure is very similar. First, the ontology detects if the battery warning is within the fault threshold and if the mission should stop. In our demonstration showcase, this is the decision that the ontology took. Otherwise, the robotic platform warns the human in the loop about the risk to the mission resilience via the digital twin and continues with the mission. Each warning displayed in the digital twin gives the human in the loop the opportunity to stop the mission during runtime. The runtime reliability ontology ensures that the autonomous system has the capability to self-certify its systems to ensure the resilience of the mission and safety of the robotic platform. The aim of the digital twin graphical user interface is to simplify the controlling process and enhance operator safety and trust by demonstrating a virtual operational preview. We present a stage 4 digital twin, which uses simulation carried out on real-time data to predict future behaviours. Colour-coded warnings notify the operator of the health status of components of the deployed robotic platform. Warnings can be set by the operator depending on the type of mission, ensuring the integrity of the robotic platform is maintained. The manipulator arm status is also accessible to the human in the loop via a meta function of the digital twin. The arms can be simulated where the fault status can be visualised within the synthetic environment with relevant colour coding for areas where a fault may have occurred. Trajectories and planned positions of the arms can be visualised by the user as a translucent ghost model, allowing the operator to preview and understand the requested operation. This function becomes useful in the scenario of our remote observer, as the manipulator arms can be simulated before committing the program to the real-world robotic platform in the field, enabling for trust that the manipulators will act as intended. Lastly, a motor fault is displayed in the digital twin with possible explanations for the fault on the left panel. A mixed reality headset can be used for remote diagnosis of faults leading to enhanced hyper-enabled situational reporting. In this demonstration, a motor fault is induced on the robotic platform. Runtime diagnostic information from the robot is fed into the model, where the ontology detects the fault and converts it into actionable information for the human in the loop, accessing the digital twin. Frequency modulated continuous wave radar sensing was the non-destructive test utilised for asset integrity inspection of corrosion on infrastructure within the demonstration showcase. The benefits of FMCW radar include lightweight, non-contact and real-time diagnosis of surface and subsurface defects. The sensor was applied to a decommissioned wind turbine blade, which exhibited a Type 4 delamination defect on the internal surface of the blade. The FMCW radar sensor was applied to detect the delamination defect and 3 mL of water within the delamination to replicate water ingress. The Asset Integrity Dashboard currently displays a 3D model of the decommissioned blade in an interactive, digital, synthetic environment. Information is displayed clearly due to the colour coding of the blade, where the red hatching displays the defective area. A tiered level of information can be acquired from the operator about the status of a fault. Upon clicking through the tiers, the operator can view further information such as radar response and descriptions from the asset integrity inspection. This investigation displays results from the FMCW radar sensor for a healthy section, delamination section, and the delamination with 3 ml of water included at 3 minutes and 40 seconds into the investigation. The value created from the Asset Integrity Dashboard enables for effective understanding of faults and evidence-based decision making, which makes sense of the complex data from the FMCW radar technology. This enables wind farm operators to better understand an overview of their wind farm and have better judgment for when remedial action is required. Mobile systems are designed to be utilised in complex scenarios which include environments which are hazardous, opaque, GPS denied, and with restricted communications. To ensure resilient autonomous systems, accurate sensing modalities are required to ensure our adapt and survive paradigm is adhered to. The multifunction of the FMCW radar means it can be used for asset integrity inspections and also for resilient robotics by ensuring autonomous systems adhere to safety compliance. The environment which autonomous vehicles will be deployed inherently have risks associated with the surface of the ground. The FMCW radar sensor enables for non-contact analysis of surface and waypoint conditions. This information is valuable for the safety compliance of a vehicle to prevent failure by avoiding surfaces which have oil, ice, or are unstable. The FMCW sensor was investigated for the signal response to 20% salt brine solution on hot rolled asphalt. The salt was deposited in the sensor field of view and allowed to fully evaporate before the same volume and concentration of salt was reapplied. Subsequent applications display increased amplitude responses with clear sensitivity to the application of residual salt from the previous brine deposition. The following application investigates FMCW sensing for human proximity alerting. This enables distinguishing humans and an asset or structure by the robotic platform. The FMCW sensor remained in a static location where firstly the back wall is represented by the blue block. A 700 by 500mm metal sheet was incrementally moved towards the radar and is displayed as the yellow blocks. The investigation was then repeated, however a human was in the field of view of the radar and moved towards the sensor. The data collected presents a difference in return signal amplitude where an algorithm can utilise the peaks collected and produce a reflection magnitude relative to a set baseline, in this case the back wall at 6 meters. The following use case demonstrates the capability of FMCW detection through walls. This initial work was conducted to assess whether the FMCW radar could be used to increase the situational awareness of a robotic platform to variables such as a human or robotic platform entering a room or mission space. This level of situational mapping promotes the safety compliance of autonomous systems when operating in constricted, high-foot traffic areas. The FMCW radar was positioned in the field of view of a partition wall where a 30 by 30 cm copper sheet was held by a human at position A on the other side of the wall. The human then walked towards the sensor, keeping the copper sheet in the field of view from the other side of the wall until pressed against the wall at position D. The figure displays observed peaks within the return signal amplitude from the empty reference baseline, indicating where the copper sheet is detected by the radar. The red, green, black and cyan peaks indicate positions A to D respectively and demonstrate the detection of the copper sheet when moving towards the radar whilst obscured through the wall. In achieving our symbiotic system, we designed and demonstrated the following: a runtime reliability ontology for self-certification which is platform agnostic, adaptable and scalable, a real-time digital twin which includes clarification of mission status, system certification and data sharing through bidirectional synchronization, FMCW radar sensing for asset integrity inspection of corrosion and delamination in a wind turbine blade, our symbiotic digital architecture which addresses operational, functional, planning and safety challenges with a top-down view for resilient autonomous missions, and lastly, a confined space autonomous inspection mission utilising a ClearPath Husky A200 robotic platform with a pair of UR5 manipulators. To further advance the roadmap from an adapt and survive to an adapt and thrive paradigm, our research will focus on the development of distributed intelligence to explore new optimizations that come from operational disruption in the stochastic offshore environment. The real value add is in the symbiotic system architecture that will host bidirectional data exchange and advance the goal of servitization, further advancing the roadmap to trusted autonomy, self-certification and safety compliance in the offshore environment. To access our full publication, simply search Symbiotic System of Systems Design for Safe and Resilient Autonomous Robotics in Offshore Wind Farms in IEEEXplore. To view more of our research, please see links to our YouTube channel, Smart Systems Group website and Heriot Watt portal.